So in this video, we're going to be looking at combination circuits. And combination circuits are exactly what they sound like. They are a combination of resistors or devices that are in series with each other and a combination of devices that are in parallel with each other. The equivalent resistance with combination circuits means that we have to switch between how we add resistors in series and how we add resistors in parallel. If we have a small group of resistors that's in series, we add them together the way they're added in series. If they're in parallel with each other, then we have to add them in parallel with each other. We absolutely cannot do them all at once. So take a look at this picture. We can see a small segment of a combination circuit at the very top. So one of the first things we do is we draw our circuit kind of in a straight line.
With this all straightened out, we can see that we have some things in series and some things in parallel. The easiest thing to do is simplify the things that are in series with each other, because in series it's easy to do. So you can see the first two that are circled, 3 ohms and 6 ohms, they're in series with each other, so we add them together. 3 plus 6 is 9. The other group that's circled is 6 ohms and 2 ohms. They are also in series with each other, so we add them together. 6 plus 2 is 8. On the next line down, we have a simplified circuit. And I recommend drawing every step of your simplification. Draw it every time, because we're going to need some of this information when we go back and we solve for each resistor and each the voltage drop across each resistor and the current through each resistor.
These intermediate pictures will be very useful. So in this second circuit, we have 8 ohms and 4 ohms in parallel with each other. So 1 over 8 plus 1 over 4. This one is going to be 3 over 8, which we then take the inverse again, is 8 divided by 3, which is 2.666 repeating, so 2.7. And then now we have all of these resistors in series with each other, so we add them like they're in series with each other. So we have 9 plus 2.67, or 2.7, plus 1, so we get 12.7 ohms. Sometimes there won't be anything in series to add with each other, so you'll skip straight to step 3, and you switch between steps 2 and 3 until you're all down to the equivalent resistance. And then once you have the equivalent resistance, you'll start working your way back up, finding the voltages and currents. So let's see what that actually looks like. So our first example is pretty simple, pretty straightforward. We have a 36 ohm resistor and a 12 ohm resistor in parallel. This parallel arrangement is connected in series with a 3 ohm resistor. This combination is then placed across a 12 volt battery. So that one's fairly straightforward and fairly simple. Go ahead and pause the video to try and draw the circuit. Once you've drawn the circuit, if you want to check, you can start the video up again, and then we can work through the rest of it. At any point in time, I strongly recommend pausing the video, trying to work the problem by yourself, and then starting the video again so that you can check your answer. So our first example has a 36 ohm resistor and a 12 ohm resistor placed in parallel. And this parallel arrangement is connected in series with a 3 ohm resistor, and then that whole combination is then placed across a 12 volt battery. So what we should do is we should start off with the first thing it says. It says a 36 ohm resistor and a 12 ohm resistor in parallel. In parallel means we get a choice. So we have some wires come in, and then we choose, and then we go out. So it should look something like that. 36 ohms, 12 ohms. If you reverse those two resistors, it's okay. If the 12 ohm resistor is up here and the 36 ohm resistor is down there, that's fine. So next, that's in series with a 3 ohm resistor. And then we connect that to a 12 volt battery. Oops. So, now that we have a picture, we have to find the equivalent resistance of the circuit. So the first thing we should do, we don't have any easy things in series with each other. We have to start with this parallel group. So to find the equivalent resistance in parallel, we take the inverses. So we would have 1 over 36 plus 1 over 12. And we can do that by hand. So we could do 1 over 36 plus, to get the same common denominator, we would have 3 over 36, which equals 4 over 36. But remember, 4 over 36 equals 1 over the equivalent resistance. So 4 over 36 is not our answer. Our equivalent resistance is 36 over 4, which equals 9. And we can do that on a graphing calculator or any other calculator if we want. So what we would do is we would have 36. Graphing calculators have the button right here to the -1. I prefer doing it this way as opposed to dividing it because there's less likelihood I'm going to get an error. But remember, this is not our answer. We have to take the inverse again. 9. You can also do 1 divided by 36 plus 1 divided by 12. Take the inverse again, 1 divided by our answer, 9. So it just depends on how you want to use your calculator. So let's redraw our circuit. We've found the equivalent resistance of that group, so we can redraw it as a single circuit, or a single resistor. And it's still connected to our 12 volt battery. So we have the 3 ohm resistor and a 9 ohm resistor. These two resistors are connected in series with each other. And in series, we just add the resistances. Nothing funny with taking inverses. So this is 12 ohms. So we have 12 ohms of resistance and across a 12 volt battery. So we found our equivalent resistance. That was our first step after drawing the circuit. Now we need to find the total current in the circuit. To find current, we're going to use Ohm's law. Voltage equals current times resistance, and which means current is voltage divided by resistance. So, voltage divided by resistance, we have 12 volts for our whole circuit, and for our whole circuit we have 12 ohms of resistance. So in our total circuit we have 1 amp. We have 1 amp of current going through this circuit. Now, to find the voltage drop and the current through each resistor here, we need to start looking back up at our next circuit up. So how are these connected to each other? These are connected in series. And what stays the same in series? Does the voltage stay the same for each resistor in series, or does the current stay the same for each resistor in a series? In a series, the current stays the same. Because remember, current is like how many runners we have. So if we have one runner running the race, that means one runner has to go through this obstacle, and one runner has to go through this obstacle. So we know the current for this one is 1 amp, and the current for this one is 1 amp. Now, this one is a little special because it's not just one resistor. It is a parallel combination, right? So when we look back up, we've got to do something else up there. But first, let's find the voltage. So voltage is current times resistance. And what I mean by voltage is the voltage drop across those resistors. Or in this case, the group of resistors. So from here to here, how much will our voltage change? So voltage is current times resistance. Current through this resistor is 1 amp, and the resistance for this resistor is 3 ohms. So 1 times 3, that one's going to have a voltage drop of 3 volts. What about for this group? From here to here, we have a current of 1 amp go through this group, and this group has a resistance of 9 ohms. So in this case, we have 1 times 9, which is 9 volts. And we can still check this by using our property for resistors in series. In series, the voltage should add up to be the total voltage for that situation. In this situation, we have 12 volts. 9 plus 3 is 12. So we know we're on the right track. Now, look one step up. This resistor and this resistor are the same. So we know that the current is still 1 amp for that resistor. The voltage is 3 volts. Over here, we've gone from this resistor to a parallel group. What stays the same in parallel? In parallel, the voltage stays the same. So that means for this resistor, from here to here, we're going to still lose 9 volts. Same thing with this resistor here, 9 volts. In parallel, the current has to split up. So if we have some runners come in here, some of them go this way, some of them go that way. So to find the current, voltage divided by resistance. For this branch, this top branch, we know the voltage drop is 9 volts because it's in parallel. The resistance in this branch is 36. So 9 divided by 36 is 0.25 amps. Do the same for down here. Current equals voltage divided by resistance. In this branch from here to here, we're going to lose 9 volts. The resistance in this branch is 12. So 9 divided by 12 is 0.75 amps. And in parallel, what do we know about the total current? The total current should be however much current is in each branch added together for however many branches there are. So we have 0.25 and 0.75, which equals 1 amp. 1 amp came into this group, and 1 amp should be distributed between the branches. This is another example. So this one, I've already got it drawn out. We have, if this was described or written down, it would probably be described as a 100 ohm resistor is in parallel with a 250 ohm resistor, and this parallel group is in series with another parallel group with 2 branches, and on one branch there is a 350 ohm resistor, and on the other branch there is a 200 ohm resistor. These 2 parallel groups are connected across a 24 volt battery. Again, first thing you're going to have to do is find the total resistance. Pause the video, find the resistance, start back up, check your answer, and then pause the video again and find the total current. We'll also be solving for the voltage and current across each resistor. Our second example already has the picture drawn for us. So this is our second example. We've got a resistor in parallel with another resistor, and that group is in series with another parallel group, and they are across a 24 volt battery. So this is 24 volts, this is 100 ohms, 250 ohms, 350 ohms, and 200 ohms. Just by looking at these numbers alone, you can kind of see that for this one, we don't want to find the equivalent resistance by hand. So the equivalent for this resistance for this one is 1 over 100 plus 1 over 250. So I'm going to use my calculator for that one. 100 inverse plus 250 inverse equals, so this is 0.014, but remember, 1 over the equivalent resistance is not our equivalent resistance. We have to take the inverse again. So inverse of our answer. So our equivalent resistance for this group is 71.4 ohms. For the other group, we can do them both at the same time because there's nothing in between them. They're just two parallel groups. We can do them at the same time. So this is 1 over 350 plus 1 over 200 0.0079-ish. But remember, this is not our answer for the equivalent resistance. Take the inverse again. So 127.27 ohms. So redraw the circuit. So now we have this one and this one. So this one is 71.4 ohms. This is 127.3 ohms. These two are connected in series with each other. So if you have a graphing calculator that can do this, you can just grab those two numbers depending on your graphing calculator. Try to keep as many decimals as you can until you get your final answer, because it will reduce the amount of rounding error you have. So this equivalent resistance, so we have a resistor over here. This resistor will be 198.7 ohms across a 24 volt battery. So we've found our equivalent resistance. The next step is to find the total current. So if you think you can do that on your own, please pause the video and then press play when you're ready to check your work. So current equals voltage divided by resistance. When we're trying to find the total current, we need to use our equivalent resistance and the total voltage for the circuit. So this is 24 divided by 198.7. So our current is 0.12 amps. Now, the next step is to try and find the current and voltage through each resistor, which means we're going to have to find some information on this circuit and find some information on this circuit. One thing that I didn't show you on the last one is sometimes it's very useful to draw a chart. So what you're going to need for your chart is something for the source or total, and then one row for each resistor. So we've got a source, voltage, current, resistance. So R1, I'm going to call this one R1, 100, R2 in ohms, in amps in volts. R2 is going to be 250. R3 is going to be 350. And R4 is 200. So, what you can do is you can pause the video and try to work through it on your own. Try to fill out the chart as best you can as you go along. I think it's going to be a little helpful, and you'll see why in a second. And when you're ready to check your work, go ahead and unpause the video and keep watching. So the first thing we need to do is, from this picture, we need to look now at this picture and figure out what's going to stay the same for these two resistors from this information over here. So in this picture, how are they connected to each other? These two resistors are in series. So what stays the same in series? In series, the current stays the same. So that means we know how much current we have through each resistor. We're going to, or in this case, a resistor group. 0.12 amps for both. We can't quite fill out this chart yet. We can fill in some of the chart. We can fill in the total current and the equivalent resistance. But this information is not going to be able to contribute to this chart. Not yet. So now we can figure out the voltage across each resistor group. Because remember, this resistor represents this group, this resistor represents this group. Voltage equals current times resistance. So we have a current of 0.12 amps going through this resistor. So we have the voltage drop across this one should be 8.63 volts. And because all of these numbers are not clean or pretty, I'm having to round. Just keep that in mind. Current times resistance for this one. The current through this resistor group is same thing because they're in series. And the resistance of that group is 127.3. So this voltage is 15.37 volts. So now, thinking of this information, but bringing it up here, between this resistor and this one, and these two, what is going to stay the same? How are these related to each other? These two are wired in parallel, and in parallel, the voltage stays the same. The voltage drop across each branch will be the same as the total voltage drop across the whole group. So for each of these resistors, we know that there will be a voltage drop of 8.63 volts. So we know we can fill in over here for those two, 8.63 for both of those. Now we can find the current. We know anytime we have two of these boxes filled in, like we had here and here, we could solve for the current using Ohm's law. Same thing if we have current and resistance. We could solve for the voltage using Ohm's law. So in this branch of our resistor, our current is going to be the voltage of this branch divided by the resistance of this branch. So we have 8.63 divided by 250. So that should be 0.035 amps. And on the other side, we could do something sneaky, because we know that these two branches, how much current has to go through both of those branches combined. Both of those branches combined should have a current of 0.12 amps. So if we wanted, we could subtract 0.12 amps minus 0.035 amps. Or we could keep solving through Ohm's law. So I'll do both and we'll check it. So the voltage drop through this branch should be 8.63. And it's the same as this because they're parallel branches. And the resistance in this branch is 100 ohms. So we get, in this branch, I'll write it over here, I'm running out of space, 0.086. So if we add those together, 0.086 plus 0.035, it's not exactly the same, but that's what I mean by rounding error. So we've had to round quite a bit in each step, which means that we can be a little off. But this is still very close to our total current going through that branch. So in the next group, you've had an example of how I did it here. It's going to be very similar for this group here. Pause the video and see how you do. Okay. So, remember, we asked ourselves from here to here, what stays the same and why? So we looked at this group and we said, oh, they're in parallel. What stays the same in parallel? The voltage. So we know the voltage for these two branches should be the same. And since there's only one resistor on each branch, we know that the voltage across this branch is going to be the voltage drop for that resistor in that branch. And down here, we have the voltage for that branch, or for that group. So we know that this should be 15.37 volts for both of those. Now we can solve for the current. I'll write down 15.37 volts. current is going to be the voltage divided by the resistance. So we would have 15.37 divided by 200 for this branch. So this should be 0.077. And for this branch, this should be 0.044. And I think there's again some rounding error. So if we have 0.044 plus 0.077, it's about the same. We have a little bit of rounding error from here. So this is another fairly simple example. It's a little different from our previous example, and you'll see why when you start finding the equivalent resistance. Draw the circuit, find the equivalent resistance, make sure you pause the video and try it on your own. So our next example is fairly simple, but it can get a little tricky. So try to draw the circuit, find the equivalent resistance, and find the total current, and then find the voltage drop and current through each resistor. So the picture for this one, we have a 9 ohm resistor and a 3 ohm resistor connected in series. So we have 9 ohms and 3 ohms. This series combination is connected in parallel to a 6 ohm resistor. This combination is then placed across a 12-volt battery. So there's two ways you can draw this. You can either extend the wire straight down and connect it to the battery, or you can have the wires extend a little bit out and connect it to the battery. Both of those are fine because you're not changing this configuration here, and you're not adding any extra resistance. So I'm going to draw it, I like to sometimes draw it this way, just to be very obvious. You don't have to if you don't want to. They're both the same. And this is a 12-volt battery. So that's how the circuit looks. So now what can we combine? The first thing we can combine are these two. So these are connected in series, and in series we just add resistance. So we would have 9 plus 3. So the equivalent resistance of this branch is 12 ohms. So let's redraw that. So we have the 12 ohms of resistance here and 6 ohms of resistance here. We didn't change anything about this resistor. And then we have 12 volts of the battery. How are these connected to each other? These are connected in parallel. So we have to add their resistances in parallel. So we have 1 over 12 plus 1 over 6. This one would be easy to do by hand if you want. So we have 1 over 12 plus, to get the same common denominator, we would have 2 over 12. So this is 3 over 12. But remember, 3 over 12 is not our equivalent resistance. Neither is 1 over 4. our equivalent resistance for this parallel combination is 4 ohms. So now we need to find the equivalent resistance. No, we found the equivalent. Now we need to find the total current in the circuit. So current, when we're finding the total current, we use the total voltage for the circuit and the equivalent resistance of the circuit. So we have 12 divided by 4, so our current is going to be 3 amps. Now look back at this picture. What is going to stay the same for these two resistors in this combination? How are these connected to each other? These are connected in parallel. So what stays the same in parallel? Voltage. So how much voltage are we going to lose from here to here? Well, we can go from the battery through that resistor group and then back to the battery. So that means we must have lost all 12 volts through that path. Right? 12 volts. That just got to be a mess. 12 volts. Same thing here. 12 volts. So how much current is going to go through each circuit? Or each branch? We know we're going to lose 12 volts through this branch, and the resistance in that branch is 6. So the current going through there is 2 amps. Now before we go on to the next one, I want you to think, if you were an electron, would you want to go through a 12 ohm resistor or a 6 ohm resistor? Remember, resistors, the number of the resistor is kind of like the difficulty for the electron to go through that obstacle. So in this case, more electrons should want to go through the 6 ohm resistor, which means the current should be greater through this 6 ohm resistor, and current should be less through the 12 ohm resistor. So current equals voltage divided by resistance. So we have 12 divided by 12, which is 1 amp, which matches what we were saying. Also, we have 3 amps of resistance total, so that means, that makes sense, right? We have 3 runners going through, starting our race. 2 runners decide to go this way, which means that 1 runner is going to decide to go that way. And then when they come back, we have 1 runner, 2 runners, so we'll have 3 runners at the end. Now from here to here, what did we change? We know 6 ohms. We know everything from the 6 ohm resistor. We know that the current is going to be 2, and we know that the voltage should be 12. The voltage drop should be 12. What about here? This branch and this 1 resistor represents these 2 resistors. How are these 2 resistors related to each other? Those 2 resistors are in series with each other. And what stays the same in series? The current. So if we had 1 amp of current go through this branch in this picture, that means we're going to have 1 amp of current go through this resistor, and 1 amp of current go through that resistor. And then voltage is going to be current times resistance. So we have 9 times 1, which is 9 volts, and 3 times 1, which is 3 volts. And how do we check things in series? The voltage should be the total for however many voltages we have. We know that we lose a total of 12 volts from here to here. 9 plus 3 is 12. So we've got all our answers. And so our final example. This one is a bit of a doozy. So make sure you're pausing and trying to figure it out on your own often. So this one's the trickiest one. Try to get as far as you can at each step before you watch the video. So the first thing to do is draw the circuit. So we have in combination, there is a parallel group with 3 branches. So we know we've at least got a parallel group with 3 branches. One branch of the parallel group has a 3 ohm resistor, a 1 ohm resistor, and a 2 ohm resistor in series. The second branch has two 2 ohm resistors. In the third branch has a single 12 ohm resistor on it. So let's add those numbers. This was 3, this is 1, 2. And then we have, these are both 2, and this is 12. This parallel group is connected in series to a 3 ohm resistor, a 6 ohm resistor, and a 1 ohm resistor. And then that is all connected to a 36 volt battery. So the picture should look something like this. If you have any of these branches kind of flipped around, that's okay so long as the entire branch is flipped around and not just single resistors. Same thing with these resistors. You can put them in different places so long as they're on this main wire. And for this one, I am definitely going to draw a chart. So let's have the source total. And then we have 9 resistors. So we know our source for the voltage is 36 volts. And then we should also fill in the resistance for each resistor. I like to go, for the resistance, I like to go according to what was mentioned first. So this will be 3 ohms, 1 ohm, and technically if you have the unit written in a chart, you don't need to rewrite the unit over here. So now we have to find the equivalent resistance. So let's go back to our chart, our diagram. We can solve for each series equivalent resistance. So let's clean up all these things in series with each other. So this one, and this one. We can do all of those at once. So we'll have 3 branches. And we'll have this one over here connected to a 36-volt battery. So in series we can add them together, so 3 plus 6 plus 1, so that's going to be 10 ohms of resistance there. 3 plus 1 plus 2, that's 6 ohms of resistance there. 2 plus 2 is 4, and then we have 12 ohms of resistance there. So the next one would be this parallel group. So we'll find the equivalent resistance of that group, and then we have this 10 ohm resistor left over. So this one, 6 and 4 and 12, we could find that by hand. I'd rather not, simply because I want to save a little bit of space on my piece of paper. So we have 6 inverse, because they're in parallel, plus 4 inverse, plus 12 inverse. That's the same as doing 1 over 6 plus 1 over 4 plus 1 over 12. But remember, 1 over 5 is not going to be our answer. We have to take the inverse one more time. So this is 2 ohms of resistance there for this group. These are in series with each other. So we can just add these together. So we have a 36-volt battery and 12 ohms of resistance for the whole circuit. So then we can go back to our chart and we can fill in the resistance. So we have 12 ohms of resistance for our total circuit. Now for current, we have current is voltage divided by resistance, so we would have 36 divided by 12. So our total current is 3 amps. Another thing I'm going to do for this is I'm going to add in some dotted lines for our different groups. So here is a division between our resistors, which were in series, and our parallel groups. But we might also want to add in some for our different resistors in series with each other in each of the branches. So we have this one and this one. All right, that's just going to help us a little bit. So our next step is to figure out from here to here what is going to stay the same. So from this picture to this picture, we know that these are in series with each other. So what stays the same in series? It's the current. So we know that the current through this group and the current through this group will be the same. Current is going to be 3 amps. Current is going to be 3 amps. That doesn't help us yet for our chart, because these both are groups of resistors. This one represents this group of resistors. This one represents this group, which represents this group of resistors. So we can't fill in the chart yet. We kind of can if we want to be speedy, but let's take it slow. Voltage is going to change across these because these are in series with each other. Voltage equals current times resistance. We have a current of 3 and a resistance of 10, so this is 30 volts. Current of 3, resistance of 2, so this is 6 volts of resistance. And what do we know about the voltage in a series? It should add up to be our total voltage. So far, so good. Move one step up. What has stayed the same completely? This has stayed the same. So we already know the current and voltage for that resistor group. We have current is 3 amps because we didn't change anything from here to here for this resistor. And we know the voltage is going to be 30 volts. From here to here, we did change some things. So how are these resistors connected to each other? These are connected in parallel. And what stays the same in parallel? The voltage. So we know that this 6 volts is true for each branch. So we know the voltage here is 6, voltage here is 6, and the voltage here is 6 volts. From here to here, we're going to lose 6 volts. From here to here, we're going to lose 6 volts. And from here to here, we're going to lose 6 volts. So how much current goes through each of those branches? So current equals voltage divided by resistance. The voltage in this branch is 6. The resistance in this branch is also 6, so the current is 1 amp. Here we have voltage divided by resistance, 6 divided by 4, which is 1.5 amps for this branch. And for this branch, six divided by 12 is 0.5 amps. And how do we check those numbers? So these numbers, 1, 1.5, 0.5, should add up to be the current going through this group. And how much current went through this group? 3 amps. So these 1, 1.5, 0.5, that adds up to be 3 amps. So we're still, so far, so good. Now, some of these numbers we'll be able to add them into our chart. So let's take a look at the next step up. Let's start over here. This resistor represents these 3 resistors here. How are these 3 resistors connected to each other? They're connected in series. And what stays the same in series? The current. So however much resistance is, or however much current is going through this representation of all 3 is going to be the same amount of current going through each of them. So we can fill that in on our chart. So we had 3 amps of current going through this resistor, which means 3 amps of current are going through each of them. So over here, this was resistor 7, 8, and 9. So we can fill in 3 amps, 3 amps, 3 amps. Now, seeing that we've got a little gap, but we've got 2 of them filled in, we can use Ohm's law to figure out the rest. So remember, voltage equals current times resistance. So 3 times 3, this should be 9 volts. 3 times 6 is 18. And 3 times 1 is 3. So, and I'm going to make a note of that to the side. This, if we add these together, 9 plus 18 plus 3, we get 30 volts. Does that match with some other numbers that we have? It does, right? We knew we should have 30 volts from here to here across these 3 resistors. And it matches. So that's good. Now what about this group over here? Let's take this one lone resistor. That looks like it'll be easier. So this one lone resistor, we've already got the answers for, because we didn't change it from here to here. So we can fill in these numbers. We have a current of 0.5 amps and a voltage drop of 6 through this branch. And it's the same up here because we've only got the one resistor. For these 2 branches, it gets a little tricky because we have the different resistors in each branch. So let's see. Let's take a look at this middle branch. So in the middle branch, how are these connected to each other? These are connected in series again. So from here, this branch, to here, what stays the same in series? Current stays the same in series. So the current for this branch is going to be the same up here, and that whole current is going to go through each of those resistors. So in this calculation, we had 0.5. So we have 1.5 and 1.5. And now we can use Ohm's law, voltage equals current times resistance, to find the voltage drop across those 2 resistors. So 0.2 times 1.5, that's 3 volts. 0.2 times 1.5, that's another 3 volts. And those 2 should add up to be 6 volts, which is the same current from there to there. And it does. So that's good. 6 volts should also be what we get when we add these 3. So keeping that in mind, let's do the next one. This group here is connected in series. What stays the same in series? The current. How much current was going through that branch? 1 amp. So that means 1 amp has to go through each of those resistors. 1, 1, 1. So now, voltage equals current times resistance. We have 3 times 1, which is 3. 1 times 1, 1 times 2. 3 plus 1 plus 2 is 6. So these circuits, combination circuits, can get very complex because we could even put parallel groups within this, and we could add all sorts of layers and just go down the rabbit hole. But hopefully you can see drawing each step is going to be helpful. Writing down the combinations for each step is helpful. Drawing a chart is helpful. But you have to always be asking yourself, what group am I looking at? How is that group related to each other? How is this step here related to the step above? What's going to stay the same for each of these compared to this one? So this is a summary of all the things that we've seen so far. We have a summary chart of our symbols and our units for each of our different things. We have a summary of Ohm's law, V equals IR, and all the different variations we could have. We have a summary of power and all the different forms of power we could see. And of course, we have our circuits and our summary of circuit properties.